Changing it, usually you have a little loop of the winding that comes out, and it's got a resin around it, which is the insulation. And so when you do that, you want to get a piece of sandpaper, non-conductive, or what they say, emery cloth, but I think that's conductive, and scrape off that little resin stuff on there. Maybe use some deox or pentox or something just to make it nice, so that when you bolt it on there, it's a nice connection. When you do that, don't crank on it, because what's going to happen, you're going to hear, and you're going to break the windings, so the resin will all crack. So you've got to grab it with, you're going to probably have your channel locks and probably either a crescent wrench or another pair of channel locks, and tighten those bolts on. Hold the one side with your channel locks and tighten the other side. And then there's a torque. There's a certain torque setting that you're supposed to do. You could use a torque wrench, or you could just go by a feel. And usually they'll tell you how many Newton meters of torque to tighten down on these lugs. Right? But I don't know how many people use a torque wrench. You guys use a torque wrench at all?
I mean,
in general, yeah, use a torque wrench?
Yeah.
Yeah, okay.
Very low on mechanics.
You adjust it? Okay, auto mechanics. Yeah.
Would you have to make those quite tight because of the vibrations?
Oh, they have to be tight.
Yeah.
Yeah, absolutely.
It might be hard to feel that.
Sometimes they've got a little, piece that they put on there. Other times it's just a loop of wire. I was trying to find a picture of that, but I couldn't find it. But on the nameplate, you're going to see, I don't know how clear that is, but you're going to see it usually doesn't show 1, 2, 3 like that, but one would be, I don't know which is which. See, that's the problem. You have to maybe read, oh, here it is. 1, jumper connection 1 is for 483 volts. Jumper 3 is for 437 volts. And jumper 2 is for 460. So what they're telling you is this, wherever this transformer is installed, that their high voltage side is rated for 460. I don't know if you guys can see that or not.
HV 460.
Yeah. Here it's 480. Ours would say 480. This might be the States. I'm not sure, or a different country. Square D. I know it's square D. But, okay, what's the frequency?
Also,
60 hertz. So it's for countries that use 60 hertz. So tap 3 means that if your supply voltage coming in is lower than 460, like it says 437, putting that onto the primary would give you the rated output, which would be low voltage. Oh, this is just a 460 in, 460 out. That's all this one is. So what they're saying is you want to bump it back up to what you should have for your machines. Then use this transformer, put it on tap 3, you're going to increase the volts per turn, and it's going to bump up the secondary voltage to 460 again. That's what it's basically used for. If it goes too high, say your voltage is like 483, and well, that's what we want, but maybe they didn't for their machine. It was rated for 460. A lot of motors are rated for 460. Then you would put it on 483. It would reduce the volts per turn, and you would get a less voltage out. You get 460 again. So the whole purpose is to get the output voltage that you want. It's not to increase it unless you do it over a long distance and then drop down again. That's how hydro does it sometimes. They bump it up a bit, and then as over a distance, because of all the loads, it'll drop down to where the customer wants it to be. So, there's another little control type. You've got options on these taps. So you might have seen this type of a thing in an HVAC unit or a fan unit. They'll have a choice of voltage sometimes that you're putting into there for the control transformers. They want 120 out, or they want 24 volts out, and you can choose, pick and choose. So you can use whatever your supply is, you want to match it to the voltage input side, and you're going to get all those voltages on the output side.
I've seen that, but it wasn't on a transformer.
Okay, where was that?
On a light.
Okay, like a ballast. Yeah, they've got a tri-tap or a quad tap ballast. Yeah, for sure. So those are transformers, and they're also ballasts, but we'll save that for the lighting section. I do two things.
So if you put it on 220, you're going to get 110 out on the secondary transformer?
or 120 or 100, yes.
Oh. Okay, so I can pick that.
Yeah, so whatever your voltage is, say you have 208 in the building,
Yeah,
or you're using it in a house and they have 240,
yeah.
right? So you can choose, on 240, you're gonna use the house voltage, you're gonna use that one. In the commercial building, you're gonna use that one, and you're gonna get the same, those same voltages.
Oh, okay.
Does everything.
Yeah, you get the
Does
same
everything.
option.
Yeah,
Oh, okay.
so. We have this in your book. Usually they're like this. What you'll find is, I was trying to find the picture of it. You can go remind me when we go into the lab tomorrow, if we get time in the afternoons, what I'm trying to do is maybe an hour, is to look at the transformer and everybody look at the taps, where the taps are on the transformer. The 100% tap is where it is factory set, and then you can choose to go either way on the taps. Usually it's the primary. Rare cases, it's the secondary. The primary is usually the high voltage side. So what would be the benefit? Why do they put it on the primary? Because you think if I increase the turns on the secondary, like if I use more turns on the secondary and don't touch the primary, I'm going to get more voltage out. More turns, more voltage. It would just make sense to do it on the secondary. Why do you think they would do it on the primary when it's the high voltage side?
Because they're stepping something up.
Lower current?
Like, why didn't they do the taps on this side? Let's say 240 volt side. Sorry, you said what?
Lower current?
Current, yeah, lower current. So the taps have a less of a chance of arcing with a huge current if it's a smaller current on the primary. So that's why they usually use the primary taps. So it's in reverse. If you reduce the taps on the primary, you're increasing the output voltage, and if you increase the taps on the primary, you're reducing the output voltage. Why is that?
The volts per turn.
Volts per turn ratio, yeah. Volts per turn, not the ratio, but the volts per turn is increased or decreased inversely with the percent tap, right? Okay. What are you doing to the ratio? So I mentioned ratio, Kyle.
Yeah.
What are you doing to the ratio of the transformer if you are reducing the percent tap on the primary?
You're bringing reducing the tap, you're having less windings with the same voltage, so your voltage is going up per winding.
So you're actually reducing the ratio. So if you think about it from that point of view, if your primary percent, if you go to 95%, you're reducing your ratio to 95% of what the ratio was before. And you're going to 105%, now you're increasing the ratio to 105% of what it was before. So in the book it gives you some really crazy formulas, but we're gonna do something easier to understand. In the book it shows this. It says the transformer ratio, they call it A. I don't know why they call it A. But the transformer ratio is basically this. You already know that, right? That's what the ratio is, and they call it A. So when you're looking at your book and you're trying to make sense of it, A is just plain old transformer ratio. That's what they tell you right there. Then they have A sub A. Bigger. So this is the transformer ratio. At the 100% tap. This A sub A is the adjusted transformer ratio. Right? That's all that little A means, adjusted. You've adjusted it. So I don't know why they go into this. I don't remember learning it this way when I was an apprentice. When I first taught this level 2 course, I was like, what the heck is A sub A? Somebody liked the method and put the formula in that way. But it actually works. All it is the turns ratio is percent tap times the turns ratio. It's the percentage of that ratio. So the adjusted ratio, they say, is the percent tap as a decimal, of course, right? Percent tap times the ratio. I'm gonna make sure. Yes. And that's for a primary tap. These are all for primary taps. But no, that's not. Let's say this one is for primary tap. Meaning that the taps are on the primary, the taps are on the incoming supply. If the taps were on the secondary, then you would take the ratio and divide it by the percent tap. But don't worry about that one. If you look at it over here, they give you that one. They say if the tap's in the secondary, you're going to take the ratio and divide it by the percent tap. That one is very rare. Okay, the one we use the most is this. It's the percentage of the ratio. So if you think about it this way, the new ratio, or the adjusted ratio, is the actual voltage ratio. So this adjusted transformer ratio is the actual, meaning what's happening right now, not what it's rated for, but what's happening, the actual voltage ratio. Which is also the new turns ratio, right? You're adjusting the ratio. So I'm putting it over there because that's what's actually happening in the circuit. It's once you use the percent tap. Okay, what if I use 100% tap?
Just use the.
Then the adjusted ratio is it's 100% times 1. It's actually really simple. I'm trying not to overcomplicate it. So then if we go 95%, whatever the turns ratio was before, let's say we had 2400 volts to 240 volts was my transformer ratings. These are the ratings for Zombla. What is the ratio?
10 to 1.
So, ratio,
Don't use the adjusted transform.
and we're going to apply, we're going to make this a step down. We're going to make it a step down. So then that would mean primary would be 2400 over 240. Easy, right? So far so good? I see some yawning, so yeah, so far so good. Yep.
Why is example 1 say 2300 volts is applied 300
Ah.
Where do you get the 24?
They just tell you.
Oh, I'm just making an example.
I don't think you
Oh, is it? Okay. Which one are, where are you looking?
Example 1, it's right on the thing there.
Oh, it is too, okay. They gotta tell you the actual transformer. Okay, I don't know, figure one, okay, I see. Figure 1.
It's the first. Yeah.
There it is, 2400 to 240, okay. Yeah, good. So the ratings, right, these are the ratings, means what's stamped right on the transformer. If you use those exact voltages, it'll be 10 to 1. It'll always be 10 to 1 if you use the 100% tap. So if you had 2300 volts, you're going to only get 230 volts out. You're going to get, it's a 10 to 1 ratio, so you're only going to get 230 out. So, but if you apply it to the 95% tap, now they want to know what do you get out of that. So you gotta know what the new ratio is. So you go 95% of 10 to 1 is what, 9.5 to 1, right? So you go 9.5 to 1, and so then you just divide that 2300 by 9.5 instead of by 10, and it's gonna be bigger, isn't it? Well, the output voltage would be bigger.
It's 21 volts.
It's bigger than
We're doing
230.
it. Oh, we're doing it off 230.
Yeah, okay, well, he was asking the example, so I was.
218.
There it is. 242. So you get more than 230 out because you use the 95% tap. So I'd be really happy with that voltage. I don't care about 2 volts. 2 volts is great because you're going to drop it down anyways when you load it up. This could be your no load voltage, right? And that's of course going to drop down anyway. So it's you're happier to even go a couple volts over. Not in theory, but in practice, more so. Yeah. So that's why I don't want to overcomplicate it. Let's look at another example. 102.5% tap. So they've taken the ratio of 10 to 1, and now it becomes 10.25 to 1 instead of 10 to 1. So you times it by, oh wait a minute. Oh, this is in reverse. Okay, so what they're saying is, you have 240 volts on the secondary. What is the voltage on the primary? So here, let's try that. 240 volt secondary. I'll do it like in pictures, you know. So we've got transformer. And then the actual voltage I'm getting is 240 volts, but this is on the 102.5% tap. So whatever taps, right? It's on the 102.5% tap, and the 2400 would be for the 100% tap. So we must be having a lower voltage or a higher voltage. What do you think? It's probably higher than 2400, so that's why they went with the other tap, right? So what you do is you take this percentage and use just this formula here. You say, okay, the adjusted ratio, it's not 10 to 1 anymore. The adjusted ratio is 10.25 to 1. So 10.25 divided by, 10.25. So basically you're going to take this and times it by 10.25. So just get the ratio, get the new ratio, and then multiply it to get the primary, or divide it to get the secondary. I'm trying to just keep it simple. Easy? What kind of voltage do you get?
2460?
2460? Okay. Equals 2460 volts on the voltmeter up here. That's my answer, 2460. Make sense? No? Okay. Good. And if you want to think of it this way, for actual voltages, the actual voltage ratio the actual voltage ratio will be the new turns ratio. Voltage in, voltage out. It's the actual voltage that you're getting, not what it's rated for. And you get the rated turns ratio, and if you have, say your question only has turns, you can deal with the turns and get your actual, what's happening, what it should be at 100%. So I'll put that at 100%. I don't know what's easier. This is probably just as easy. This here. It's the same thing. Okay. Large fault currents. One last thing. I spent too much time on this. Larger transformers have quite a bit of fault current. As we've seen in some of the calculations, fault current can be really high. If you get a short circuit, it can be very damaging. So if, to help control the damage, they take the windings from the center rather than from the ends with larger transformers. So it doesn't really matter to you. You've got A, B, C, D, E, F connected, and you sort of, two of them have to connect. If C and D are open, then you have two windings that are disconnected. Right? If it melts the center of the winding, you're not short-circuiting to ground a higher voltage. You're short-circuiting halfway, let's say, half the voltage. So the idea is to, if the weak link is the tap, then you're going to have, if the tap is open or whatever, a short circuit either may exist or may not exist. But if it does exist, it will be less voltage to ground because you're halving the winding, you're taking it apart in the middle, right? So what you can do is you can take C to D. Okay, let's see. Each one of these is 90%. What does it go? This one goes, it's a little bit different. It goes from 90 to 100. So I guess what they're doing is, this one is only for increasing voltage. This one is a little bit different. It doesn't have 105% tap. So let's say, okay, but what they're saying is that percentage is not what the winding would be labeled. That percentage is the effective part of the turns. How many turns are effective here on the primary? 100% of the turns would be probably the 105% tap, right? With all they're at this chart, the percentage they're giving you is the effective part of the winding. 100 might say 105, is what I'm saying, like in reality. So let's see, C and D would be 100%. Then if you take B and D, you're subtracting, was it 2.5? Yeah, 2.5. So either B to D or E to C would give you the same, right? Take out one little part, few turns off one side, there's 2.5%. So they're saying each portion is 2.5%. So what if I went from A to F? Don't look at the chart. A to F. 10% less, so it's 90% of the windings effective. Yeah. So you could say, it might have a little chart like this. This might say 105, 102.5, and 100 might be B to E. Right? That's kind of what I'm getting at. Okay. Easy?
Yes.
Let me know. So there you go. There's some self-test questions on that.
No.
Auto transformers. Okay, I'm going to erase this.
I don't even know what question to ask.
Okay?
Wait,
That's a
Mo? Take a picture.
Kyle says, thank God Ron spent forever last time.
No joke. I don't know. I was probably sleeping.
Which was kind of embarrassing because you were sitting right at the front.
Yeah. You know, I think I used to sit where Alex was at. Jeff was. I can't remember. I think I was in Jeff's seat. Yeah.
Oh, great. This is the seat's cursed.
Check if that have boogers still under there.
Okay, why would you want to use an auto transformer rather than a dual winding transformer or an isolation transformer? Why would you, like this is a dual winding, it's also called isolation transformer, this one up here on the board. So, an auto transformer means it has one winding.
Oh,
So
yeah.
that's all it needs. So you can have like,
Just normally just pick where you want it.
it looks like a big inductor, and then they decide to take out wires like this, and we're going to call this our primary. And not our secondary. But we only have one winding. So what would be the purpose of having one winding? Well, they're smaller. Auto transformers are a lot smaller. So for space, they work the same, and I'll get into the operation of them, but the purpose of auto transformers is for small, like they're physically smaller and you can fit them. That's not in there, it's further down. But there's 4 other reasons. They're normally used in situations where all you need is a small increase or decrease in voltage. So this might have some taps, right? We might have some taps off different points of this, and all I'm going to do is increase or decrease depending on where I tap into the turns. Okay, if I tapped into all the turns, basically, I don't even need the transformer. It's right off across the supply. So for reduced voltage starting is one of the biggest ones. So a squirrel cage induction motor, like this motor, only maybe a 3-phase motor usually, but you could use it on this motor too. You have an auto transformer to reduce the voltage on a very large motor so that you don't get a huge inrush current when it starts up. So you'll have a set of contactors. So you use a couple of contactors, and one of them will be in one configuration will take it through the auto transformer, and then the other configuration will be across the line. Right? So it'll be this contactor pulls in initially when it starts, and of course your control circuit has to be made that way. So then now it's starting using the transformer, now it's across the line. So what it does it for the first maybe a few seconds, and then it goes, and after that it'll run with line voltage.
Does it,
Yeah.
So what using that as contactors, does it parallel the transformer with the motor so that it splits the current? So less, is that kind of how it works? Not really.
All it would do is it would take these two, let's say these 2 lines went through the contactor, and then when the contactor opens up, there'll be another contactor that pulls in across the line. So it just, in parallel, I guess is best, that's what you mean?
Yeah.
Yeah,
Yeah.
parallel options.
Yeah.
Yeah.
So the parallel splits the 2 paths of
That's
current.
right. We'll wait for level 3 to get, you'll get big time into that. That's all about reduced voltage starting, different values. But as for circuitry, not even bother, just understand that that's what it's used for. In power supplies where multiple voltages are required, so lighting ballasts here, lighting ballasts are multiple voltages. This one here, this 100-watt metal halide tri-tap ballast has 347, 277, and 120. And so it does this. I'm not sure if it uses the full thing. Yeah, because you're going to supply, you're going to supply it on this side. Anyway, if this is the supply, this is the primary, this is the line, this is the load, just reverse it. This one has 120, 277, 347. So it uses an auto transformer. And you can see that on this exact diagram. There's more to it. There's other things connected to it, like the lamp and the igniter and the capacitor and all that stuff. But that's the basic diagram for this. And this one they call the common. Anyone who wants ballasts?
Yeah.
Okay, so it doesn't mention lighting ballasts, but power supplies where multiple voltages are required, maybe like say a transformer, like a control transformer, you might have like the one we saw earlier, the one I brought up here, I think. Maybe this one. You have options, right? So different options for power supplies, but that's a dual winding. So all it would be is that you would have, this one would be gone, and you'd have it connecting into the same coil, the same set of windings. Problem with that, there's no isolation. There's no cushion for any high voltage spikes. There's not a, all the circuits are connected, so you can't use it in an auto transformer in every application. A dual winding transformer is better for keeping the power separate from problems, from let's say disturbances from the line and things like that. But auto transformers do have a place. In fact, we use them quite a bit. Okay, automatic voltage regulators for line drop as load changes occur. So maybe those on-load tap changers. So what taps are they changing? A lot of times it'll be to boost it up at a substation or something. Boost up the voltage at the substation and carry it along a lot further. So here's one, and we'll get back to this one. They label this A, B, and C. So A to C is the line voltage, 100% of the voltage. If this was center tapped, say that it's center tapped, half the turns, if I stab a voltmeter into half the turns, I'm going to measure half the line voltage, right? So if I had, let's say, 240 volts, and this was the exact number of turns, we had, let's say, out of 100 turns, we had 50 turns here and 50 turns here, then the secondary voltage that you would measure from the center point to here would be 120. Right? But there's a couple things that are different about this than what we did before. When we had, you know, say this had 100 turns and this had 50 turns, we could get the same thing, 240 into 120. But there is a common wire, this letter C. Letter C doesn't need the transformer at all to my load. It's directly connected to the, let's say if we have line 1 and line 2. Then line 2 would carry right through. It's common, it conducts. It's the conducting part of the transformer. It's not even part of the transformer. Only part of the transformer is from either A to C, A to B, B to C, but C is the common factor, right? The energy in this is almost like this. You need all the turns to produce volts per turn in the core. So this core flux has to be produced with all these turns, right? Or I could make this my primary and put a lower voltage across half the turns. I would get the same volts per turn. So the key is to volts per turn have to be a constant, have to be proper. So how do I word that? Correct volts per turn must be established for flux. How's that? To produce correct flux. So wherever you tap in, it'll say you have to use this voltage. Oh, here you got to use a bigger voltage. this little tiny bit here, you can use 10 volts. You know what I mean? So whatever it is, you gotta get the correct volts per turn on this transformer. It's almost like an inductor producing a number of volts per turn. That's exactly what it does. Now when I connect into this 50 turns here, I've got 120 volts. But if I'll get into it in a second, okay? I'm probably getting ahead of it.
Oh, I was so excited there.
Oh yeah, I gotta go through this.
Yeah.
This is the key. This is the key right here to all of auto transformers, whether they're single phase or 3-phase or 3-wire secondary or whatever you get. Doesn't matter how complicated it looks. Go right back to this every time. VA in equals VA out. If you use that, and you do it properly, you'll get the right answer every time. Because as long as you're ensuring that the VA out is the same as VA in, you'll have it right. And then you got to use other things with a Kirchhoff's voltage law, current loss, and that sort of thing. So VA in VA out. If you can get one of them on one side, think of it as a primary and secondary, even though it's connected to the same thing. If you think of it that way, if you get one side, you've got the other side. And now you just have to say, how does that work? What's the missing current, for example, right? EP over ES equals NP over NS, IP over IS equals NS over NE, right? So nothing new there.
Wait.
Wait.
Let me write it down.
Step down. Why did they call it a step down?
Going down in voltage.
In the textbook.
Yeah. My primary here is a higher voltage, so I step down because I've tapped into less turns, and this is where my load would be. The other situation is a step up. So they got to step up. I could make this my primary, the other one my secondary, and put my load over here. 240 volt load I can run using 120 volt primary, using an auto transformer. There's only one winding instead of two, so it can be physically smaller. Okay. Yeah, here's a good situation. You know how you have a lot of heaters that are rated for 240 volts, and then the building will have 208. So if you work out the power on that, it works out to 75.11111% of the power that you get out of the heaters, only 75% when you use 208. So if you use a step-up auto transformer, you can do that in your dryer, you can do that on range, you can do that on tanning beds. I've been in a tanning salon, we put them in the back of an auto transformer to step up the voltage so that it gets the right light and the right heat that you want. Right? Otherwise it operates at 75%. So that's an application there, and they're physically smaller so they can fit in like a junction box or a ventilated type box. But usually the box, you're looking at something fairly large. Still, it's not the best thing to have this transformer kicking around on the back, like behind the tanning beds. Anyone work in those tanning places at all? No? Yeah, service calls. I've done tons of service calls, and you get the weirdest calls, I'm telling you.
I think stories are getting the tan on.
Yeah, one place they said, Ron, I'm going to send you to a Chinese restaurant. So I go to this Chinese restaurant, and it wasn't a Chinese restaurant, it was like a massage place, and I don't know what kind of massages they were doing there, but, anyway. Yeah, so you get the weirdest service calls. The girls were saying it was a little slow, so I was like, no, that's okay, I'm married man.
Hopefully that story had a happy ending.
So learn about auto.
Out. The door.
I'll follow that one.
Multi-tap. There it is there. this circuit here, if you're using it for lighting, if it's used for lighting, you have a grounded circuit conductor. Which one is the grounded circuit conductor if you're using it for lighting?
Bottom?
Bottom, it has to be bottom, because you're trying to maintain, what is the grounded circuit conductor, first of all? Grounded circuit conductor. What color is it?
You need white.
White, neutral. Okay. Gotta get the lingo. Grounded circuit conductor is the neutral. Okay, the identified conductor, right? Same thing. It's secondary, and you must solidly connect that according to the code. So solidly connecting that, making sure that you don't have your neutral up here. If I say I had 120 volts in, I must put the neutral on that bottom wire. I cannot put it on the top wire. It will work, but it will be dangerous, right? And yeah, especially if these would have a certain potential, you can throw everything off. It's like reversing hot and neutral when you shouldn't. So this is important to maintain. So if I have 240 volts, or sorry, I have 120 volts in, this one here, here's another situation, and I want to create a 3-wire circuit. So if I have 120 volts in this case, I have to put the neutral on the center conductor, because that's going to be the neutral, and it's going to carry right through. So I can actually step it up to 240 in this case, but I cannot put the neutral here. I have to make this one the neutral because it's fixed and connected right through to the other side. You see that? So now you're going to produce, the volts per turn you're going to produce will be the correct volts per turn because you're only energizing half the winding's volts per turn. And what will happen to the rest of the turns? If I energize 120 on the left side, and I get so many volts per turn, what is happening on the other rest of the windings? They will get the same induced voltage because the core is causing that to happen on all the conductors. So it doesn't matter what part of the coil you energize, the rest of it is going to develop that voltage. And it's like a new source. So you're adding another 120 volts because they've say it's 50 turns and you got another 50 turns. You've added another 120 volts so you can get 240 out. That's a little bit of a brain stretcher for some at first. But if you think about what's happening, it's the core that's doing the transformation to the rest of the windings. They become a source, and that will be the opposite polarity to the other wire at the bottom. So, and that'll be the center point between it. You just produced a 3-wire circuit. Okay. For simplicity, it says the core is sometimes not shown. But you have to understand that it's always there. Yeah, if I started drawing it on this one, I would have my wire going through my core. So we just kind of, after this, we just kind of eliminate that from the picture. Variable auto transformer, figure 6A. 6A? Oh no, 6. Figure 6. That's figure 5. Oh, I see. Figure 6 is, okay. Variable auto transformer, where do you think you find one of these? Yeah. You've used one. For the past 2 years. For 2 levels.
Calculator.
It's a bit of a stretch. I'm not going to say no, but not what I'm looking for.
On the Ellsworthy bench,
Yeah, the Ellsworthy bench. So when you're increasing the voltage, you're going from 0% to 100%. You're tapping. It's a wiper, and it's contacting, and you're producing. That's a variable supply. Right there. So you already used these. Looks a little different than the picture, though. So they correlate these letters with the diagram. D is the wiper, and then you have, I believe, C to A is the complete thing, it looks like. And then what's B? It's the winding. Is that the halfway point? Okay, let's see.
One,
Oh, it's not halfway.
the 1-to-1 ratio.
Okay, so where do we put the power in? Where do I put the power in? D, oh, that's a secondary. So my power in is B to C, it looks like.
Yeah.
B, that's weird. So for whatever reason, it's B to C. And this is why?
Oh, because it's going around the other way, it's going counterclockwise and counterclockwise.
Okay. So in this case, the wiper, so I can get more voltage than my supply gave me, or I can get less voltage depending on where the wiper moves to. So that's it. You're just tapping in at a different spot with a sliding contact. That's it. Oh, it does say test benches.
Yeah.
Ah.
It also says calculator.
At B, the transformer is 1-to-1. Okay, let's see, 1-to-1. Oh, that's what they're saying. So if D joined to B, we went like this. Into here, 1-to-1 ratio. This would be 1 to, well, more than 1, it would be like 1 point something to 1. And this would be, what, bigger, the second number would be bigger. 1 to 1.2 or something, right? So we go up a step up. Next. What do you think so far?
Fine.
I don't know what I think.
Okay.
I don't think.
I think I need to do an example.
Test, he said.
Let me look at the samples I have. The amount of current will be the same. Okay. So 240 volts, 600 turns. We could use volts per turn, or we could figure out. Oh yeah, I think that NP over NS, we could get the ratio. So what's the ratio? 600.
1.15.
Okay. So NP over NS in this case is 600 turns over 5. 20 turns, and what did you say that was?
1.15.
1.15 to 1, right?
Yeah. So it's like 208.695 volts on the 10.
Is this to scale?
Not really.
It would be more like up here, wouldn't it?
Yeah.
Okay, so if that helps, draw it that way. If that helps you, you can draw it that way. Now you can see, oh, okay, I see, I only got a little bit of turns left there. It might visual would help, right? So if you draw it differently, okay. So if I take 240 volts, what do I do? Divide or multiply by 1.15?
Divide.
Okay, so I take 240 volts, divide by 1.15.
208.6.
Oh, I did it wrong. I'm wrong.
What is that?
One job. 208.69 even?
2.8695652.
Yeah.
Okay.
Does not give you your VA.
5 decimal places or memories, right? Okay, so we take that and we take our 10 ohms using that full number, gentlemen.
Storage, alpha A.
What kind of current do you have coming up? If you have 208 across that load, it's going to be 20.8, but is it going to be what, 20.86
20.86956.
amps? Okay, and you store that number. Okay, now you say, okay, well, how many VA out is that? So this is the key. This is the key.
Keys.
Get the VA out.
It's 4,355.3603.
Okay, and store that number. Now, you got the VA out, how do I get the VA in?
It's the same thing.
Put an arrow. There you go, it's the same.
Crazy.
So far so good? Like it? I like it. Love transformers. Okay, robots and disguise. So you go 4355.36 VA, and now what do I divide it by to get my current on the primary? 240. So 240 gives me how much current?
18.147. Oh, that's important. 147.
18.147 amps. Okay. And the VAs should equal. Okay. Let's give it some polarities. Use orange. I don't know if you can see the orange very well.
Nope.
I'm going to make this negative because I gave it that direction, and this one positive, instantaneously. So what happens here is that this top part of the winding is more negative than the bottom part of the winding. So that's negative and positive. Okay. When I drop down, right, this one still over here is the common wire that connects right through. So it is the most positive point in the circuit right now. It's ground level. I've dropped down. I'm still more negative than that point, but by less volts, right? By 208 instead of 240. So that is negative there. So the current, I got the correct current direction through this load. I've got the correct current leaving the source, and let's draw it coming back. And I would recommend you do this every time. Always do it this way. Yeah.
Well, I think on the box they make a mistake finding the current for secondary.
Oh, what did they do?
They did 208 amps. It should be 220.8.
Oh, did they do 208 amps? Okay, so it's a typo. Let's see where.
Yeah, it's just.
Yeah, 0.8. Just put a decimal there. Yeah,
I
are you
was
good?
doing it as like
Yeah, thanks for fixing it. Maybe if you send that in, you'll get a Home Depot gift card. I don't know if that one's worthy for the gift card, but send it in. You go to BC Trades modules and say report an error and tell them the level and the binder and the page.
I don't know if you're serious or not right now.
I am serious.
Well, I found better on D4 was something wrong on the examples too.
Well, tell them.
Remember the one we did?
This whole book is wrong.
I'm gonna go. I don't want that.
I actually, every year, twice a year, we go through those error reports. I'm part of the committee, so I know this is a true thing.
And also on D4, there's one of the examples. There's an error.
Don't give it away.
I don't want to set it in. I know that's
Who likes to get there?
$5.
They didn't say. It's, one organizing it is from Thompson Rivers University in Kamloops, so I'll have to email them and say.
I know
By the way,
Kamloops was like,
Anyways, off track here. 18.147. Okay. 40. What's the current? How much current is leaving this node and coming back?
20.
Make sure I put my decimal. Okay. Now, question. At this node here, when the current splits off, I have 18 coming in and 20 going out. So which way and how much did the current have to be at that point? Into that node or out of that node?
Whatever the difference is.
Okay, what's the difference between these two numbers?
I don't know.
Percentage?
18, 44.
You got them stored, so
2.7225.
okay, 2.7225 amps.
Yeah.
Okay, in this part of the line. Okay, all right.
Would it not be in the small part of the line?
No,
No, 'cause that's
this
where-
current is coming into here.
I got
This
that.
current is
Okay,
going out.
got you. I see.
So which way does this current have to go? Out or in? In. You have to
In.
inject it in there in order to get it out, right? Okay, so it's coming in. This is a source to that load. It's the same polarity, negative, positive, all the way down. But this part is conducting. This part of the winding is called the common part. Oh, sorry, is it that part? No, hang on. Common part. The common part is this part. Sorry, the common part is this part to both circuits. Sorry.
Oh.
Ah.
Oh.
This one is in series with the load. This part of the winding is the key, though. This part of the winding here it's in series with the load, is it? Yeah, kind of is. It's a little bit different. Okay. Anyway, this is the total current in the circuit. Total current in the circuit is there, 18.147. However, how did I get more amps out?
It's like your control, you can go up and add it.
This volts per turn that was maintained through here, this volts per turn, produced a voltage here that supplied this load. It was less voltage in this case, but more amps. So it needed to produce all those amps from this winding and add to what was coming from the source. I know it's a weird thought, but the VA in equals the VA out, doesn't it? So it has to be true. That's how you deal with these. The key is to get the VA out with your load, plant it on the VA in, and divide it by the primary voltage. And you'll be able to figure out the remaining part of the winding and what it's doing, regardless if it makes sense to you or not. It's happening and it's true. Okay? And that's the key to level 3 three-phase transformer, auto transformers, which people are like, ah. It's like, no. VA in is VA out, and then all of a sudden they get it. So it's not as complicated as you think. It's just weird, right? Right? Okay. Yeah, 2 amps, 3 amps. But this is actually like a source, an additional source for the load. Even though it's also a load source, the actual source, it becomes a source.
So if we kept so if it changed that onto the coil spot, if we were to move it down, let's say, the amperage in that would change as well, right? It's becoming a source. Like if we moved it from
Yes.
this spot.
Yeah, because less voltage, you actually have to get more current out of it. If you go, what if I went straight across the line? How much current would be in the winding? What if I put it onto the top here and made a connection right here?
It's either going
I'd
to
have
be
240 volts on the load. I'd have 24 amps. What would the transformer be supplying?
When it just like your 18.147.
No. What if I did this
Is it 40?
instead?
It just equal out.
It'd be the same,
It's a 1-to-1.
240 volts.
So 240 would be 24 amps. How much would the transformer have to supply? Zero. Be right off the source.
Yeah.
So the transformer would just be creating magnetizing current at that point.
Ah.
Okay? Let's do a step, let's do the opposite. We'll step up. They're really cool. Transformers are cool because they're weird. And you understand them, the principles. Okay. 43, 26 VA, is that what we got? Well, they got way
If it wasn't
different.
down on the corner.
See what you get when you round?
Yeah.
Look what they got. Idiots. And it didn't even equal. I really hate this book. But they always say, oh, we use 3 sig figs, and yeah, but you round everything all along the way.
We used to do
Zero
things, but
amps.
we never had that many.
Well, yeah.
Here's a step up. So let's look at this one.
Who's trying to check?
Yeah, I'm already advanced.
Yeah.
Almost.
Yeah.
same transformer. They gave us same load but different voltage now, so it's gonna probably, the numbers will be different. Okay, so my supply is 208 volts. You could do volts per turn and then multiply by the, or volts per turn and then, yeah, multiply by the turns to get voltage. You could do that, or you could just do the ratio, and then, so what's your output voltage? 240. Not exactly, is it?
Yeah.
Is it?
208 times,
208 times 600 divided by 520? 208 volts times 600 over 520.
240 exact.
Is it?
yep.
240.
Didn't work the other way.
Actually,
Did it?
somebody.
Did somebody
the wrong number.
fuck up on the 1.15?
You did it.
Clay is not here.
Clay. That's why he ran, he knew.
Yeah.
They're on to me, I'm too deep.
Oh.
Yeah.
It's okay, you're not Clay. We were talking about Clay, so. Okay, so all these numbers would have been exact, more exact. Yeah, you redo that with the actual ratio. This one here should have been, if you take 208 times 520 divided by 600, sorry, 240 times 520 divided by 600, you should get 208, right? Yeah, okay. Anyway, whatever. It is what it is. So this is 240 volts.
Is that half mark?
No, that's.
He only gets a half mark.
F minus.
Actually, it's wrong, right? Okay.
So brown.
How much current is that? VA out. So we want, how much current is this?
24 amps.
24 maybe?
24 amps. I'm gonna. Okay, I'm not gonna put the direction. I'm just gonna put that. And we'll say, what is the VA?
Trouble guys here.
You screwed up.
You fired, dude. Get your shit.
You had us using the 1.15 instead of the actual ratio. We
Oh.
screwed the whole thing up.
Put it in the voltage, man. That's for the ratio.
How are you gonna sleep in that, dude?
Now we can't do the quiz tomorrow.
You're kinda like that guy who would say that other guy from drowning but didn't.
What's this, 5760 or something? Or what is that? Okay. What's the VA in?
Oh, it's the VA. Okay.
5760.
So far, so good? These are really easy. Okay, 57, as long as you just follow the steps. 5760 divided by 208, how much current?
24 amps.
27.69. I'm going to make this one negative and this one positive. So 50, sorry, I lost it.
27.69.
Okay.
Amps times
Okay.
600 turns.
And 24 amps here. Okay. Well, if this is the most positive point in the circuit, then that means that the current should be going this way. Back to the source. Or should it? Let's try it. Let's try it. So let's say that's positive, because it's the most positive point in the circuit. It has to be. They're connected,
Yeah.
right? So that's negative. Did everybody agree? Yep. Okay, awesome. So this is 24 amps going in this way. This is 24 amps coming out that way. And this winding here is receiving 24 amps from this node. So, question.
3.69.
What's the difference between 27.69 and 24 amps?
3.69.
3.69, okay. 3.69 in this winding. Which direction?
Up.
Up. Down.
Down.
Has to go down. going in,
Come on,
you got
Buckhurst.
28 cars going in and only 24 coming out here, so the other
They gotta
4
be coming
out.
out.
Right?
That's right.
Awesome.
What?
So this now becomes the load to the source because the current is going in the proper load direction. Here becomes the source. This becomes a little positive negative source. It became more negative. It produced this part was the source in the circuit, this little tiny bit that added to make 240 volts out of it. Where's my 240? Right here. We only had 208. So it's an additional voltage that was added to it, made it more negative, all the way up to 240. And I think if you think about it in that way, just think of the common point is the most positive or whatever, the other one has to be more negative. Yeah.
The coil, does that become like a source, or shouldn't it go positive to negative?
Yes, that's exactly what I just said.
Well,
Hey, Mike.
is it where your node is, that's where the source is?
From the node to the top, from here to here, this is the new source. How's that? And you're adding it in series with the old source.
No, I just thought it was
Yeah.
the 3.69 that was the new source, not the 24.
Sorry? 10.69?
Never mind.
No, this becomes a load because the current's going from negative to positive. Just think about which way the current's going.
Yeah. Alright.
Just think about it.
If you don't label, if you're not meticulous and you don't label, you'll screw it up.
Technically, yes.
It's usually how that happens. You'll subtract the current instead of adding the current. If you follow the steps and are methodical about it, you will never screw it up. You'll be able to see that it's wrong and you'll fix it. Right? So anyway, that's how I do it every time. And I just like, I don't remember things. I just like, let's work with it and build the puzzle, and then does it look right? It has to be right. Because everything, all the rules work.
I like to force some pieces though.
It's from another puzzle.
Yeah.
Here's a multi-tap, example 3. Okay, let's look at this one. 12240 lighting system. It's a good one.
I was thinking around the first one. What I did.
You rounded through.
Oh, well, yeah, obviously I abandoned it.
This should have been exactly 208 volts. He's gonna try it now.
No, it's not though. Yeah, I know with that.
Stop.
No, you
I'm pretty sure it's 1.1538461.
208.
Times that.
Well, on calculator it says 208.695.
No, you just rounded to
Yeah.
it.
Yeah, I just rounded it, but I mean, I didn't know we were going crazy or anything like that.
Okay, okay.
I test that.
It's okay, we talked about you while you were on. Yeah.
I'm surprised you came back.
Yeah,
It's okay, but you can fix your example in your book.
Oh,
You have the example.
Sorry,
Don't
January,
worry.
but after my back wants to
no.
What's the key? What's the key to auto transformer calculations?
The VA out is the VA in.
Yes.
Unless you're in the textbook.
What's the lock?
I admit, for a kid that's so smart that you test.
I don't know, it's stored somewhere.
Like,
How many?
Just never promised anything, right?
What was it for you?
I went into the
Knock on
code final at 72, bombed the code final, went into the actual final at 67, came out at 62. Unlucky! The worst part was when Ron stared me in the face and said, "Kyle, you only have to get 74 on your final." And I was like, "I can do it." Ron said, "You can do it." Boom, 57%. Actually, he didn't say that. He said, "Don't bother coming anymore." See you next year. I'm retired if you're coming back. Told him I was going to BCIT. I got him.
Why is this one the neutral?
Cause it's supplying
It's the grounded
both sides
conductor.
of the parallel circuit.
Is that wrong?
Grounded circuit conductor, and because it has to carry on as the neutral on the other side. So it's the common wire to everything. There's actually two common wires in this circuit, line 1 and neutral, but then there's a new one, wire C.
Would that just be line 2 then?
It would become line 2, yeah. So over here, this one is line 1, this is neutral. Now you got a new one called line 2. Absolutely. Okay. They give negative and positive. Okay, I'm not going to look at the diagram. Let's work it together. And we've got the solution in your book. Let's look at the board and kind of work at it together. Do this in 5 minutes. Okay, line 1 will make negative, neutral will make positive. So current has to go there and back. Correct?
Yes.
Okay. I've got a few different voltages. These are exact number of turns. So this would be like 50 turns or something, right? Who knows? 1,000 turns, 1,000 turns, they're the same. So 120 volts will be reproduced over here by the core that's not shown, and we're going to produce another 120 in series with it. So this would be negative, positive, right? This would produce the most positive point in the circuit would be the other side. This one is obviously the most negative point all the way through. So this side has to be the most positive side all the way through. Correct?
Okay.
That's how I do it. These are all negative. This is the highest negative energy level.
That makes sense.
Right there. Okay. So the currents will always go from negative to positive through the load. So all the arrows will go down like you've always done in all 3-wire circuits. And we've got 12 amps flowing in here. 10 amps flowing into 12 gives us 22. And then it goes up this way, 22. Okay, now we'll go to the top. Say I got 12 amps coming out, 8 amps going down. What came in? 20. Okay, 20 amps came in. And then I've got 8 amps going in, 10 amps going out. So the neutral must have had 2, and it went to the left.
Yeah, right.
No, right.
Shouldn't-
To the left, to the left.
8 amps came in.
Right. Yeah. All you doubt me.
I just wanted to sing some Beyonce.
Okay, so level 1 stuff. Looking at without the transformer, it's just 3-wire circuit. Same as before.
I just wanted to see.
1.15.
Alright, does it work? 22 amps comes back on line 2. Don't even look at the transformer, just say 20 and 2 go that way and 22 comes back. Yeah, the neutral carries the unbalanced load only. Okay, nice. Okay, this is the weird part. I've got 22 amps coming in, 2 amps coming out. I need to know how much current I have over here first. So what you gotta do, what's the key to solving transformer questions?
VA equals VA.
We need the VA out.
VA equals
We
VA.
need
Good
to
job.
get the VA out. I would stop there and just get that. The next step is if you don't know the current or direction, get the VA out right away. So the VA on this one is, what's the voltage here?
120.
120, so if you want to remind yourself of that, you can draw a little voltmeter.
288.
Why is the
And this
bottom
one's 240, right?
Yeah.
Why is the bottom what?
120? Isn't that parallel like the whole circuit?
The bottom is, because the number of turns is the same as the volts per turn up here, it's produced that many volts per turn again on that part of the transformer. The core is doing the work, right? It's producing voltage on that loose winding there. Even if the winding was hanging out like that, and like you had the wrapper on the core and the wire was loose, you'd have 120 from that point to there, and you have like voltage sitting there not connected.
Okay.
It's actually dangerous to have that. Okay, so we've got 120 times 8 is what? 960?
Yep.
960 VA?
Yeah.
1200 VA? 24 times 12?
288. Zero, 200.
2880?
Yeah.
Yes.
2880 VA. So I'm gonna take this one, plus this one, plus this one, and get a total VA out.
Oh,
5,040.
What do you guys get?
5,040.
5040?
Yes.
Okay. But I don't know the VAN. I'm sorry. What is the VAN?
it's 5,040.
20%.
1.15.
Okay. Does everyone get this so far?
Yes.
Okay, it's a 5. All right, so having this VAN at 120 volts is how much current?
42.
Sorry?
42.
42 amps? That's a big single pole breaker circuit right there. I don't think you can get a single pole 60 amp breaker or whatever you need for that, right? Anyways,
Make one.
regardless of that,
Black market.
it's from a panel or whatever, so, okay, 42, now you can do Kirchhoff's current law, or as they say in Germany, Kirchhoff, right? And you say 42, you gotta do that, right? I think it's, anyway, 42 minus 20.
Got everybody good.
Did you talk like that when you were in Germany, or did you do your accent when you were there?
Yeah.
I would have done my accent when I, well, I would have done your accent when I was there.
We're short, like, near.
22 amps, that's only in Bavaria, they don't do that in Berlin. They're different there.
Wait, why is there?
They're all artists and philosophers.
Yeah.
Why is it being up 50, where do we get 5,040?
So is this correct?
2880?
Is this? No, you got 1, 2, 3 all added together.
Oh, you added it, okay.
Yeah.
Okay, that makes sense.
Okay, awesome.
Yeah.
Then we divide that by 120, got 42 amps. So that at node A, we've got 20 amps leaving, 42 coming in, so we must have 22 amps coming down. Okay, we have 22 amps coming up, and just
2
check
amps leaving.
node B now to make sure that that 2 amps actually works. Does it?
Yeah.
So 22 plus 22 is 44,
Minus
and then subtract 2 is 42. Yeah, perfect. So that's how you solve these things. What is the VA of the auto transformer required for this? The whole transformer.
Is it,
If you add up the VA of this winding and the VA
is
of
it
this
10,080?
winding, right?
No.
If you take the 240, if you take 120 times 22,
5,380.
okay, hang on. 22,
Now he's
Just 120
confusing
times
us.
22, and then
Yeah.
just times that by 2, because you have 2.
because it happened twice, yeah.
Yeah.
And what did you get?
This guy.
Or you, because they're drawing the same current, you could take 240 times 22, you should get the same answer.
Yeah.
Yeah. After coffee or after lunch, whatever break, after whatever you do in your break, foosball break, whatever it is. We're getting into buck boost connections. Now, this transformer, because it's an auto transformer, draws the same current in both windings, right? So the VAs will always be equal on an auto transformer in this fashion. But you will find a dual winding transformer, such as this one, will require much smaller KVA because most of the load is conducted. In this case, we required, what did you say, Clay, 52 something?
280.
You actually needed a bigger transformer than what you were getting out, right? But because you stepped up the voltage, you'll find that when you step down the voltage, you can actually use a smaller transformer than the VA you get out. They won't always be the same. The VA of the source is VA in. The VA of the load is the VA out. The VA of the transformer is whatever part used the transformer. Some of it is conducting directly to the load. some of it is not. In this case, more of the transformer was needed to get this current, or to get this VA, than the source could provide. And you needed a bigger transformer. It's sort of a weird thought, but we'll see those examples happen.
Is that the VA?